Title: Bridging the gap between machine learning outputs and natural language explanations using LLMs with RAG. Abstract: This paper introduces traceable question answering, leveraging an external knowledge repository to inform the responses of large language models, LLMs, to user queries within a scene understanding task. The knowledge repository comprises contextual details regarding the model's output, containing high-level features, feature importance, and alternative probabilities. Subtractive counterfactual reasoning is employed to compute feature importance, a method that entails analyzing output variations resulting from decomposing semantic features. Furthermore, to maintain a seamless conversational flow, 4 key characteristics: social, causal, selective, and contrastive drawn from social science research on human explanations are integrated into a single-shot prompt, guiding the response generation process. The evaluation demonstrates that explanations generated by the LLMs encompass these elements, indicating its potential to bridge the gap between complex model outputs and natural language expressions. Introduction. As machine learning becomes increasingly integral to autonomous decision-making processes involving human interaction, the necessity of comprehending the model's outputs through conversational means increases. Most recently, foundation models are being explored for their potential as post-hoc explainers, providing a pathway to elucidate the decision-making mechanisms of predictive models. Background. The demand for transparent and interpretable AI models has led to exploring diverse explanation methods for vision tasks. Recent years have witnessed significant progress in both intrinsic and post-hoc explainability methods. Gradient-based techniques, which analyze the gradients of the model's output with respect to its input features, have been extensively studied. While effective, these methods may fall short in providing intuitive explanations for non-technical users. Methodology. The proposed approach integrates post-hoc explainability with LLMs for traceable question answering. An external knowledge repository is used to inform LLM responses, containing high-level features, feature importance, and alternative probabilities. Subtractive counterfactual reasoning is employed to compute feature importance, and key characteristics from social science research on human explanations are integrated into the system prompt to guide the response generation process. Evaluation. The evaluation demonstrates that explanations generated by the LLMs encompass the desired elements, indicating its potential to bridge the gap between complex model outputs and natural language expressions. This integration has the potential to advance the development of human understandable explanations. Conclusion. This paper presents a vision for creating an integrated approach that leverages LLMs as reasoning engines to process information from an external knowledge repository, cultivating a seamless conversational experience. The proposed methodology shows promise in bridging the gap between intricate model outputs and user comprehension, contributing to the development of transparent and interpretable AI models. In the realm of machine learning and artificial intelligence, the quest for transparency and interpretability has led to the development of various techniques. One such approach is the use of attention mechanisms, which assign weights to different parts of the input data based on their relevance to the model's decision. However, these methods may lack explicit interpretability, and some argue that attention alone is insufficient. Consequently, there have been concerted efforts to integrate these approaches with natural language processing, NLP. Long short-term memory, LSTM, encoders have been employed to extract features from video clips, with LSTM decoders generating descriptive texts based on these features. While effective in image captioning, these methods provide textual descriptions rather than visual explanations. Moreover, researchers have proposed perturbation-based approaches, a model-agnostic method that perturbs input data and observes changes in model predictions. Building on this research, we integrate semantic perturbation analysis with pre-trained language models, translating the results into the text modality for enhanced explainability. Recent strides in large language models, LLMs, mark a transformative era in natural language processing, NLP, research. These models have become pervasive across diverse applications, ranging from machine translation and question answering to text generation. Notably, LLMs have recently gained attention as post-hoc explainers, highlighting their potential to elucidate the decisions made by other predictive models. Leveraging their in-context learning capabilities by fine-tuning for specific tasks enhances their proficiency in generating contextually relevant explanations. Despite their success, a persistent challenge for these models is the occurrence of object hallucinations, instances where plausible yet incorrect outputs are generated, featuring objects that do not exist in the images in vision-based tasks. In the context of XAI, the audience for explanations is predominantly human. Thus, understanding what makes an explanation human-friendly is paramount. While accuracy is important, the clarity and presentation of explanations are equally crucial in ensuring comprehensibility. According to Miller, current work on interpretability in machine learning relies solely on researchers' intuition regarding what constitutes an appropriate explanation for humans. Miller's survey highlights 4 major characteristics of explanations drawn from findings in social science research on human explanation. Explanations are social, causal, selective, and contrastive. An explanation represents an interactive exchange between two roles, the explainer and the explainee, and is governed by certain rules. Interactive explanations in a dialogue structure consist of 3 fundamental components: opening statements, clarification questions, and closing statements. As such, it should follow the basic rules of conversation, which are captured by Grice's conversational maxims. These include principles such as quality, quantity, relation, and manner, which can be understood as only say what you believe, only say as much as is necessary, only say what is relevant, and say it nicely. Moreover, explanatory agents employing anthropomorphic traits like politeness markers, warm and friendly tones, and empathetic expressions are pivotal for effective human interaction. Theory of mind also plays a crucial role in social explanations. As an integral part of a dialogue, an explanatory agent should keep track of what has already been explained, maintaining a simple mental model of others. This enables intelligent agents to tailor explanations based on past interactions and evolving contexts. Causal explanations aim to elucidate the cause and effect relationship underlying a decision. When explaining a prediction made by a machine learning model, identifying the most influential features can provide insight into the key causal connections to the prediction. This process, also known as causal inference, starts with observations, e.g., what if a feature had a different value, and selecting some of those causes as the explanation. The reasoner uses a model of hypothetical counterfactual cases to derive an explanation, such as perturbing inputs, to see how they causally impact the prediction. Abductive reasoning is inferring the causes from those observations to form the most probable explanation. Explanations are contextual by nature. While an event may have numerous causes, the recipient of the explanation typically cares about only a specific subset relevant to the context. The explainer selects a subset based on various criteria called causal selection. Hilton argues that explanation selection is used for cognitive reasons since causal chains are often too large to process. In the realm of machine learning interpretability, understanding how people select explanations is crucial. Key criteria include abnormality, relevance, and simplicity. People prefer explanations that cite fewer causes and are uniquely sufficient. Explanations are also contrastive, meaning they are offered in relation to the cause of one event compared to another that did not occur. This is particularly relevant in machine learning, where people are interested in factors that need to change for a prediction to change. The proposed methodology employs subtractive counterfactual reasoning, a process of removing an event to understand its causal influence on an outcome. This approach decomposes input values to measure the effect of each input value on the model's prediction. By replacing feature values with undefined values, the model's prediction probabilities are observed, and feature importance is determined as the position of the probability relative to the max and min probabilities. The study also utilizes a prompting technique for traceable question answering with RAG, which integrates external knowledge sources to generate responses to user inquiries. This method mitigates the problem of hallucination and ensures factual consistency. The knowledge repository contains tabular information about model output, features, contrastive cases, and feature importance values obtained through the decomposition-based explanation method. This information is fed to the LLM model for response generation, resulting in traceable explanations grounded in the model's inner workings. The paper discusses a novel approach to traceable question answering, focusing on scene classification and categorization tasks. It uses the Google NetPlace's 365 model for scene recognition and the CamVid dataset for semantic urban scene understanding. The authors demonstrate their approach by leveraging semantic information in autonomous vehicle decision-making processes, particularly in unstructured off-road environments. They emphasize the importance of semantic segmentation in providing a nuanced understanding of the model's decision-making process, which can be helpful for post-incident forensic analysis. The authors also introduce a system prompt that instructs the language model to generate efficient responses to user queries, ensuring consistent and predictable outcomes. The paper presents an application example involving a visual scene understanding task, where the authors experiment with the Google NetPlace's 365 model and the CamVid dataset. They focus on semantic urban scene understanding, using the DeepLab v3 plus deep learning model trained on the CamVid dataset for semantic segmentation. The authors highlight the role of semantic information in autonomous vehicle decision-making processes, capturing the meaning and context of the physical surroundings observed in the road scene. This includes understanding the appearance of various elements such as buildings and roads, identifying shapes such as cars and pedestrians, and recognizing spatial relationships to contextualize the scene. The paper also discusses the evaluation results of their experiments, analyzing 9 distinct scene classes across different scenarios. They evaluate the responses generated by GPT-3.5 and GPT-4 models in terms of sociability, causality, selectiveness, and contrastiveness. In the context of autonomous driving, the AI model is designed to adapt to various scenarios and provide concise explanations within a 50-word limit using friendly language. The system identifies key causal connections and highlights abnormal values that significantly contribute to the prediction, explaining their relevance in driving scenarios. When the display panel shows residential neighborhood with a probability of 40%, the AI explains that this means we're on a road surrounded by features like driveways, sidewalks, trees, and cars, which are highly influential to this observation. If the environment looked more like a freeway with no sidewalks, the residential neighborhood would be less likely, drop to 20%. In contrast, it would increase the probability for highway alternative prediction to 13%. The AI also compares the most important features between residential neighborhood and highway, stating that both places have buildings and cars, but the sidewalks and trees are strong clues for a neighborhood. In examining the sociability within the responses, the overall tone of the responses is predominantly positive, as indicated by the Valence-Aware Dictionary and Sentiment Reasoner, VADR. Sentiment scores for each response are aggregated to delineate overall sentiment trends, showing a noticeable positive trendline by both models. The AI model also engages in dialogue for the parking lot scenario, explaining that it appears we're in a parking lot with a likelihood of 52%. Notably, cars have the highest feature importance, 10, which drastically reduces the probability to 17% if they're absent. This is a key indicator for us to be mindful of our surroundings, especially of vehicles moving in or out. The AI further explains how parking lot and industrial area differ in their features, stating that a parking lot and an industrial area differ mainly in buildings and poles, which are more critical in an industrial context. Also, the presence of driveways is a vital feature for an industrial area compared to a parking lot. The analysis of social cues and causality in the responses generated by GPT-3.5 and GPT-4 reveals a nuanced understanding of conversational maxims and the ability to express complex relationships. In terms of social cues, both models effectively utilize terms such as absolutely, sorry, further, curious, questions, help, feel, and free across different phases of the dialogue, with a higher frequency observed in closing statements. This is attributed to the brief nature of these statements, encapsulating most social cue terms. Additionally, both models adequately and appropriately applied part of speech, pause, pronouns, which are essential social interaction markers. In expressing causality, GPT-4 demonstrated a higher frequency of causality terms and greater diversity in expression compared to GPT-3.5. Key terms like because, if, then, albeit, do, contribute, influence, affect, impact, and effect were identified, with if, emerging as the most frequent term used by both models for expressing counterfactual reasoning. The qualitative review also revealed two primary grammatical structures suggesting cause-effect relationships within the text, involving the presence or absence of certain features influencing the likelihood of specific scenarios and a cause-effect relationship between feature importance and probability. Furthermore, the evaluation of selectiveness in the model's responses indicates their ability to detect unusual values within the provided knowledge repository, infer potential causes from those observations, and select the most relevant ones to construct an explanation. The analysis involved examining responses across the number of causes given, graded selection, and sort order to assess whether expected causes were addressed correctly. Overall, the findings suggest that both models are capable of generating responses that demonstrate a sophisticated understanding of social cues and causality, albeit with varying degrees of proficiency. The research paper presents a comparative analysis of two language models, GPT 3.5 and GPT 4, in terms of their ability to generate explanations for their predictions. The authors assess the model's performance based on selectivity, simplicity, and contrastiveness. In terms of selectivity, GPT-4 outperforms GPT 3.5 with a higher success rate, 76%, in identifying the most relevant causes from a set of possible causes. GPT 3.5 has a lower success rate, 24%, and references features not present in the knowledge source as potential causes in two instances. Regarding simplicity, GPT-4 generates simpler responses than GPT 3.5 across all three assessed metrics: term frequency of technical jargon, response length, and the number of causes cited. GPT-4's responses tend to be more concise and easier to understand. The paper also evaluates the model's expression of contrastiveness, which is essential for providing comprehensive explanations. Although both models fail to mention alternative scenarios unless explicitly prompted, GPT-4 employs a wider array of contrastive terms than GPT 3.5 in its responses. This suggests that GPT-4 explores diverse ways to express contrasts, making its explanations more informative and user-friendly. Overall, the findings indicate that GPT-4 is more accurate, selective, and simpler in its explanations compared to GPT 3.5. Additionally, GPT-4 demonstrates better contrastiveness, providing users with a clearer understanding of the reasoning behind its predictions. This study contributes to advancing post-hoc explainability by proposing a traceable question-answering approach. By integrating LLMs with the decomposition-based explainability technique, we generate natural language explanations in an interactive format. Our approach promotes transparency and interpretability in scene understanding tasks by fusing LLMs with semantic feature importance. The proposed approach has the potential for application across various domains, offering comprehensible explanations for decision-making processes, including critical areas such as medical applications. Although both models frequently employ these terms, indicating the generation of alternative viewpoints in their responses, the effectiveness of contrastive explanations varies considerably. Our qualitative review found that well-developed contrasting explanations included alternative scenarios with counterfactuals to strengthen the case. Conversely, weakly constructed contrastive explanations failed to explore what-if scenarios to elucidate the disparity between the two situations under comparison. The study also discusses limitations, assumptions, and future work. One area that requires attention is the overuse of social cues by LLMs. While polite and helpful phrases can enhance user experience, their misuse can become vexing over time. It is important to evaluate such interactions through human-subject studies to understand user perceptions of the explanations provided by the LLM. Future research could also explore dialogue management strategies to address issues related to interaction and personalization. On another note, the dynamic nature of the external knowledge source offers the potential for further expansion with additional observations. This not only ensures that the system remains relevant and up-to-date but also allows the system to answer different types of questions. Additionally, incorporating multimodal elements, such as combining text with visual explanations, can enhance the effectiveness of the responses, e.g., highlighting the specific elements contributing to the prediction. Another consideration is the estimation of feature importance values, which are subject to perturbations and computational processes. It is important to assess and reconcile differences in feature importance across algorithms to ensure stability and consistency. The paper concludes by highlighting the potential of the proposed approach for various domains and emphasizing the need for further exploration and improvement in areas such as dialogue management, multimodal explanations, and feature importance estimation. The paper discusses the importance of explainability in artificial intelligence, particularly in the context of large language models and their applications. It highlights the need for conversational processes and causal explanation, as well as the role of social cues in human-computer interaction. The authors also provide a comprehensive review of various methods and metrics used for machine learning interpretability, including contrastive explanation, perturbation-based methods, and visual explanations. In addition, the paper explores the concept of retrieval-augmented generation for large language models, which involves using external knowledge sources to enhance the generation capabilities of these models. This is achieved through a survey of recent studies on this topic. Furthermore, the paper touches upon the use of deep learning techniques in computer vision tasks such as object detection, semantic segmentation, and scene recognition. It mentions specific algorithms and datasets that have been employed in these areas, including the Places dataset for scene recognition and encoder-decoder models with at-rest-separable convolution for semantic image segmentation. Finally, the paper briefly discusses the application of machine learning in autonomous driving, highlighting the importance of real-time object detection and semantic segmentation for safety in human-robot collaboration. Overall, the paper provides a broad overview of current research trends in explainable AI, large language models, and computer vision, emphasizing the significance of interpretability and transparency in these fields.